Hello everyone, my name is Jordi Sastre and I'm a PhD candidate at EMPA, the Swiss Federal Laboratories for Material Science and Technology. Here I will talk to you about the lithium garnet LLZO solid electrolyte cathode interface investigated by an old thin film model system. Let's get started. First, I would like to motivate why a thin film model system is interesting to investigate the solid-state interfaces between electrolyte and electrodes. As you probably know, thin film batteries have been developed in the last 30 years into a commercial product targeting specifically low-power applications, for example, IoT sensors or wearable devices. Besides this product application, thin film batteries are also valuable tools as model systems for research and development purposes. Thin film solid-state batteries offer almost ideal planar interfaces which can be easily accessed through a wide range of characterization techniques. This makes it a very interesting system to investigate, for example, the solid electrolyte electrode interfaces. A thin film battery is typically fabricated onto a substrate and consists of current collectors both for the anode and the cathode, an anode and a cathode, and a solid-state electrolyte. All of these components are fabricated in the form of thin films with a thickness in the range of micrometers or below. Let's have a look at the solid-state electrolyte of a thin film battery, as this is one of the key components. Typical thin film solid-state electrolytes are vacuum processed into thin films in the micrometer range. They have rather low ionic conductivities in the microsiemens per centimeter range and are typically amorphous or glassy materials. The best example is this LiPoN, lithium phosphorus oxynitride. However, the solid-state electrolytes employed in bulk systems widely differ from this type of materials. So if we want to use the thin film architecture as a model system to investigate all types of solid-state batteries, we need to adapt these bulk materials into thin films. The lithium garnet LLCO has been widely investigated in the last years as a promising solid-state electrolyte for bulk batteries, for bulk solid-state batteries. Why is this? First, it has a relatively high ionic conductivity of around 1 millisiemens per centimeter. But most interestingly, it has a wide electrochemical stability window, making it stable against metallic lithium and high potential cathodes. And moreover, it's mechanically and temperature stable. However, if we want to prepare this material into thin films, we face several challenges. First is the processing. Lithium garnet LCO requires high temperature annealing in order to crystallize it. This, due to the high surface to volume ratio of a thin film, this leads to massive lithium losses, therefore limiting the maximum temperature at what thin films can be processed. The lithium loss also tends to produce porous films, affecting therefore the density of the electrolyte. Also, it is known that LLCO suffers from surface degradation when exposed to air or moisture. Therefore, thin films are especially sensitive to this degradation. All of these challenges lead to lower ionic conductivity in thin films. Typically, thin films have shown ionic conductivities in the range of 10 to the minus 5 siemens per centimeter, which is about 1 to 2 orders below the typical LLCO in pellet form. If we look at this table here, this summarizes the ionic conductivity of both pellets and thin films, and we can observe this gap between conductivities. We also see that there is a trend between processing temperature. Pellets which are processed at high temperature show better ionic conductivities, whereas thin films which have to be processed at low temperatures have lower ionic conductivities. We developed a method to fabricate LLCO thin films with properties comparable to the bulk, Let me explain how this method works. We use a traditional or typical magnetron sputtering system with a stoichiometric LCO target, which is sputtered onto a substrate, forming an amorphous LCO film. Later, this film is annealed in oxygen, pure oxygen, at a temperature of about 700 degrees, leading to crystallization of the film. However, due to the massive lithium losses occurring during the deposition and especially during the annealing, these films show impurities in the form of lithium deficient lanthanum zirconate, which is not conductive, ion conductive. How can we tackle these lithium losses? What we do is incorporate an additional lithium oxide target in the system and co-sputter it during the LCO deposition. This leads to an overlithiated, as prepared film, which later crystallizes into a pure LCO phase. One of the key parameters of this processing is the lithium excess in the as deposited films. We investigated the effect of the lithium excess by tuning the LLZO to lithium oxide sputtering rate. As we can see here, if we deposit with low amounts of excess lithium, the films show rather good microstructure. However, the crystallinity is not pure LLCO. We have this impurity phase due to the lack of lithium. If we go to the other end, if we incorporate a massive amount of excess lithium, what we see is that the morphology is severely affected by the evaporation of lithium during processing, even though the crystallinity is pure LLCO. Therefore, this tells us that the lithium excess is a key parameter in the processing of LCO films. This has to be appropriately tuned in order to have good morphologies with LCO crystallinity. As we can see in this middle range, where a good dense film is fabricated and shows proper LCO phase. Another key parameter in the processing of LLCO thin films is the doping. As it is well known, LLCO requires the incorporation of an alliovalent element which stabilizes its cubic conductive phase. For example, aluminum or gallium. However, besides the effect of this dopant into the crystallinity, we also observe that it can affect the density of the films, the stability of the films, and ultimately its ionic conductivity. The question now is how to incorporate the substitution element into the films. In our group, we worked with different approaches. First one consists in depositing it in the form of multi-layers. Basically, depositing overlithiated LLCO, a thin metal or metal oxide layer, and repeating this sequence over multiple times. This allows to control the amount of dopant in the films precisely. However, it leads to some inhomogeneities in the dopant distribution. Another approach is to co-sputter the metal oxide in parallel with the LLCO and lithium oxide targets. This allows for better homogeneity, but it increases the deposition process, it increases the complexity of the deposition process, and it leads to a bit of irreproducibility from deposition to deposition. Finally, knowing the optimal amount of dopant, we can just simplify the process by incorporating the dopant into the LCO targets, leading to better homogeneities and high reproducibility of the process. Let's have a look now at the effect of the dopant into the film properties. First, let's have a look at the crystallinity of the films. We investigated it by Grayson Kingston XRD. If we have a look, we see that the incorporation of aluminum and gallium both leads to a almost pure cubic phase, as compared to the tetragonal phase of the non-doped LLCO. If we then have a look at the microstructure, we see that the dopants also have an effect on the density of the films, especially the aluminum doped film. If we have a look also at the degradation in air, we see that the non-doped film has a surface layer of lithium carbonate indicating some degradation occurring when exposed to air, whereas the doped films don't show this prominent surface degradation. One of the key parameters of the LCO is its ionic conductivity. To investigate the ionic conductivity in the prepared films, we measure impedance spectroscopy in an in-plane configuration and measured it over a range of different temperatures to obtain its Arrhenius plot. We can observe that the gallium substituted LCO shows a prominent ionic conductivity of 2 times 10 to the minus 4 Siemens per centimeter at room temperature. The aluminum substituted films has a slightly lower ionic conductivity of 5 times 10 to the minus 5 Siemens per centimeter, whereas the non-substituted film show ionic conductivities in the range of 10 to the minus 6 Siemens per centimeter. The activation energy of the doped films is also significantly lower, especially that of the gallium substituted film. If we put into perspective these values, we observe that our fabrication method, allows to obtain LCO thin films with ionic conductivities of about 1 order of magnitude above previously reported values, while maintaining the same processing temperatures. And moreover, the values here reported allow to close the gap between thin films and the typical ionic conductivities report for pellets processed at significantly higher temperatures. Now let's see what this LCO thin film can be useful for. One of the main issues of the LCO electrolyte is its interface with the electrodes, especially with the cathode material. Both cathode and electrolyte are ceramic materials and cannot be simply cold pressed to form a proper bonding. The bonding requires high temperature co-sintering, which leads to high interfacial resistance because of cross reactions and interdiffusion occurring during the processing. Therefore, interface modifications are required to avoid interdiffusion cross reactions and therefore limit or lower the interfacial resistance. Can we use a thin film model system to investigate this interface and come up with better solutions? We prepared a half-cell architecture in thin film form by depositing LCO thin film followed by LLZO thin film. This architecture allows to access easily the interface to investigate what is occurring during co-sintering. Greisenkind XRD shows that besides the LLCO and LCFOs, there are some impurities appearing, especially this lanthanum zirconate phase, which indicates degradation of LLCO electrolyte. If we look at the top seams, we can see that some interdiffusion is occurring, namely zirconium oxide and lanthanum oxide are diffusing into the cathode and cobalt is diffusing into the electrolyte. This model system allows to introduce interface modifications to block this interdiffusion. In our case, we employed a 30 nanometers ALD deposited niobium oxide, which is in situ lithiated upon annealing. This barrier layer allows to block interdiffusion and obtain a stable interface. If we look at the XRD, we see that after introducing the niobium oxide interlayer, the films show only LLCO and LCO phase without any impurity. And if we look into the compositional profile, we see that the interdiffusion of zirconium and lanthanum oxide into the cathode is drastically reduced, as well as the cobalt going into the electrolyte. To quantify the charge transfer resistance, we measured these half cells in a wet 3-electrode system. Impedance spectroscopy of the half cells shows the drastic effect of the interface modification in the charge transfer resistance. Non-modified LLZO, LCO half cells show an ionic transfer resistance of about 5 kilo ohm per square centimeter, which is a rather high value. Whereas in the niobium oxide modified half cells, the interface resistance is drastically reduced to only 50 ohm per square centimeter. This value constitutes a record for LLCO, LCO, all inorganic interface. We further investigated the charge transfer properties by cycling these half cells in the 3-electrode wet configuration. We compared the non-modified modified LLCO LCO stack to their LCO. We can observe that the modified LLCO LCO half cell has shows a cathode utilization as high as the bare LCO, whereas the non-modified LLCO LCO has a significantly lower capacity. In order to assess the performance of the interface at high rates, we measured charge-discharge curves at different C rates. Here we can observe the rate performance of all three systems, and we see that the modified LLCO LCO interface behaves almost as the same as the bare LCO, with capacity retentions up to 60% at 10C, which corresponds to a current of about 200 microamp per square centimeter. We also assessed the cycle life performance of these half cells. We cycled them at 10C over 200 cycles and observed a cycle life of 80% initial capacity retention of 138 cycles. This is significantly higher than typical LLCO solid-state batteries reported in literature. To conclude, I would like to show you some preliminary results on full cells employing thin-film LLCO electrolyte. You employed the half cells previously shown and used lithium metal as an anode. And the interface between the LLCO and the lithium is still problematic, resulting in high interfacial resistance at this interface. However, we were able to cycle such a thin-film battery, being the first time that such a battery architecture is presented. We will further work on this interface by introducing interface modifications, interlayers that lower the resistance between the charge transfer resistance between the lithium metal and the LLCO thin film. And here are the conclusions of my talk. We have shown that a thin-film solid-state battery architecture model system can be useful to investigate interfaces in solid-state batteries. We have shown a method to prepare LCO thin films with equivalent properties to the bulk material. And we have incorporated these thin films into a half cell with LCO cathode material and investigated the interfacial properties. We have shown that upon co-sintering, high interfacial resistance occurs due to interdiffusion and cross reactions, and a lithium niobate interface modification can significantly reduce the interface resistance to only 50 ohm per square centimeter. This allows to prove the interface transfer at fast rates. We finally showed that this architecture can be also useful to investigate the lithium metal LCO interface. With this, I would like to conclude my talk and thank you very much for your attention. I would also like to thank my colleagues from the battery team at the Laboratory for Thin Films and Photovoltaics from EMPA, and also my collaborators and our funding. Thank you very much.